Swayam Prabha. Digital India. Educated India.
Okay, all right. So we started off yesterday, and then there's a lot of similarity between the two-dimensional dynamics. Some of the uh, aspects or some of the features of 2D dynamics can be extended, but with much broader uh, implications. Okay. So, for example, this one which we are talking about, yeah, this is one example which we are talking about, is that the main vertical pillar on which the disc is mounted on a horizontal. So disc that cylinder gets the angular velocity input right from the vertical rotation as well as its horizontal axis rotation. So its horizontal axis is rotating at an angular velocity of omega-2 about the vertical axis, while there is a omega-1 about the horizontal axis. So that means that the cylinder is subjected to two angular velocities, omega-1 and omega-2, except that this more complicatedly, so they are in two different directions. So every point here will be subjected to two rotational motions. Okay. So in that process, so this also we were discussing. So any point, something like A, is subjected to a rotation because of omega-1, right? So that means that from horizontal axis, a distance up to A, so that will be multiplied by omega-1, and that will give you a horizontal velocity component. Okay. In fact, there are many directions, different points will have different. So we are talking about a point A on the vertical plane somewhere. Okay. So it will have a horizontal component. So similarly, it also gets an input because of omega-2 also. So because of omega-2 also, it will be subjected to a velocity here, something like, yeah. So from A, you measure the distance up to the vertical axis and multiply it by omega-2, and that will give you the linear velocity component. So these two, in particular for this point A, it so happens that they will be equal in magnitude as well as opposite in direction. So why we have taken that particular point is that it has a zero velocity. It has a zero velocity. Whenever something has a zero velocity, so if you recall your 2D motion analysis, so we used to call it as instantaneous center of velocity. So in 2D, it's just a point. But here, it is just not one point. There are several points which have zero velocity. So all those points are on having zero velocity. So we can as well say that it is the axis of rotation. It is the axis of rotation. So instantaneously, so the whole cylinder is rotating about the axis NN. Instantaneously, the whole, see, this is also how we say, so you have to really appreciate, now we said that this is a rotation about a point, but at any instant, it is an axis. The body, so the body will be rotating about some axis at each and every instant. Okay, so there is one line in the body which will have points with zero velocity. So all those things can be construed as a axis rotation, right? You understand? So it is just not one point. So now you can see that the whole body is rotating about point O. It is essentially, it is a point of rotation that has a zero velocity all the time. Point O has a zero velocity all the time, but then there are several points at every instant who also have a zero velocity. Okay, so they are called axis of rotation. So only thing is that this axis of rotation, just like you know that we have instantaneous center of velocity, so these points keep changing because the body is rotating. So at this instant those points are there, but at the next instant the points will change, and then another set of points will have the zero velocity and another axis will form. So like that, so these points, if you trace it on the body, then we call it as we used to call it as body centroid. Here we call it as a cone, body cone. So it happens here as a cone, but it can be a surface also. So there is, so all those points, if you trace it on the body, we call it as a body cone. And if you trace it in the space, in the fixed space, big XYZ, then we call it as a space centroid, we used to call it. Now we call it as a space cone. So that's how, yeah, that's how these pictures will look like. So in the body cone, O is of course a fixed point. So you can see that all those points will have zero velocity at some point in the as it progresses. So similarly, we have a, so that axis also keeps rotating about the vertical axis, which we call as a space cone. So like this, so that means that what more is that? So this line also happens to be the sum, the resultant angular velocity. So omega 1 plus omega 2 when added vectorially, so that will be in this direction. So this omega is a vector, omega 1 plus omega 2, and that will happen in this direction. So you can vectorially, we know that velocities, angular velocities can be treated as vectors and we can add them. So that means that, so so you can also see that since this is the axis, obviously all the points along this line will have zero velocity. Okay, that's the axis of rotation. And this is omega is a vector, omega 1 plus omega 2 as a vector. Okay, so this is just a little bit of description. I'll pass on these slides to you at the end of today. Okay, so what we have here is that, yeah, so we have a space cone in general or body cone in general. So it need not be as simple as that. It can even be complicated. So only thing is that, so since in particular, so this is a vector omega. So this omega, so in space, what happens is that it is going to travel on in a space. So whenever some vector moves along, changes its direction or changes its magnitude, we call it, it has a time derivative. If it is an angular velocity, its time derivative, we call it as a acceleration, angular acceleration. So in two-dimensional fixed axis rotation, we have axis constant, but magnitude is the only one changing, and it continues to be in the same direction. But here what happens is that it's possible that its magnitude is changing, so it may have a component in the same direction, as well as its direction is also changing, so then it will also have a tangential component. So it is a sum of these two vectors. Okay, so that's alpha. The angular acceleration is not just in the direction of omega itself, but it will have the other component also. Yeah, so in particular, so if you look at this, go back to this example. Yeah, what is happening if you go back to this example? So we have this resultant vector, angular velocity vector omega, and then it is traversing on the space cone. It is going round on the space cone, right? So whenever this angular velocity is changing its direction, obviously it is changing its direction, if not magnitude, so it is going to have an angular acceleration. So can we see a similarity of this one? So like we are saying here angular velocity, but if you think that it is a position vector, so if there is a point P here, which is traveling along this space cone, and what is its magnitude? So in the space cone, it is traveling on this circle with a center here. So its vector will be omega 2. Remember? So for this example, so that means that this omega is traveling on the space cone, right, with an angular velocity of omega 2. So the omega itself is omega 1 plus omega 2, but omega by also is rotating about the vertical axis with angular velocity omega 2. Okay, so if there is some point P here which is traveling, which is given by omega, imagine its position vector is given by omega vector, and then it is traversing along a circuit. So then what will be its velocity? How do you say its velocity? It is omega 2 cross omega. Omega 2 is the angular velocity of this omega rotating. So whenever we say, even in 2 dimensions, we used to say the velocity is omega cross r, right? Here instead of r, we have omega itself. Instead of r, we are having we call it, instead of the position vector, we have a omega itself. What is omega? So you measure it from here to here. So omega itself is the position vector. So, okay, so we are going one step further. We are generalizing. So this is all what, so that's what it says here. So if this is the total angular velocity vector omega, and then this big omega is the one omega 2 in this particular example. It can be something else also. It may be rotating about something else also. The space cone may be rotating about some other magnitude. But here it so happened omega. So in general, we call it as a big omega. Okay. So the angular acceleration now is nothing but omega cross omega here in this example. So like this, so we have this is in general. In this particular case, we can give that as big omega cross omega. But in general, what do you say? If omega is the angular velocity, if you want to find out its time derivative, then we call it as angular acceleration. So here, this may have 2 components. So this is just like your linear velocities. So this has a parallel as linear velocity. V is omega cross r, A is equal to omega cross omega cross omega cross r. So this has a, so then we have to do that also. We'll see that. So there is exactly this same thing whatever we have discussed. So we can see it as an example. So here, let me tell you. So you should be comfortable dealing with several kinds of set of axes. So some we use as big XYZ. We call it as a fixed system. Then there is another small XYZ. Okay, we may per convenience, it may be attached to the body. Okay, so and then the total time derivatives are with respect to small XYZ, then you have to bring it to big XYZ. You know, we have dealt with all kinds of moving and rotating frames. Okay, there's a translating frames, then there's a rotating frames, and the same concepts we have to bring here also. Okay, so let us try to understand this problem. So the exactly it's similar to the problem which we have been discussing. Exactly same thing. So here what we have is that let me explain this problem. So we have a disc here attached to the motor, and the motor is spinning with a certain velocity given by 120 per minute. So there is a motor which is rotating. So that means that its angular velocity is z, small z. Okay. So there's a big XYZ, there's a small XYZ. So big XYZ usually horizontal XY and Z, big Z. And here also we have chosen Z axis vertical so that this mounting, the motor mounting, is rotating with an N about the vertical axis. So that means that now you can realize that the disc gets input from 2 angular velocities. One is the velocity about the vertical axis, and the other one is the spin of the motor. So it will have just like almost the same examples which we are calling. You can call it as omega 1 and omega 2. So we have a spin velocity. So for convenience, this is the one where you should be able to convert from one coordinate system to another coordinate system, taking care if the system itself is moving. Okay. So here in this particular case, in this particular example, what he has given is that there is a big xy z, z is vertical, xy is in the horizontal plane, and then this small xyz, we fix it in such a manner convenient to us. So what is the convenience? So we'll put small z in the direction of the spin of the motor. Okay. And then we have another small x and small y. So what is this small x-axis and small y-axis? These are perpendicular to z-axis. In fact, what is this small xy? In fact, small xy is also a plane representing the disk. So the disk is also in the plane small xy. So we have that. So that is the convenience part, because anytime, so the disk can be represented very easily in the small xyz, whereas big xyz will give you the absolute velocities and absolute accelerations. So we should know how to convert from small xyz to big xyz. Okay. So let us see. In fact, I'll go back to that. But to start with, the total angular velocity of the disk can be thought to be a big omega. So big omega is the vertical axis about which the whole motor assembly is rotating. Okay, which we called as n RPM. And then this another omega naught is the velocity of the disk, spin velocity. Okay, so the thing here, you should see that these two vectors are not they are vectors, but they don't refer to the same axis. For convenience, they are not referring to the same axis. So that means that we have to, then I'll go back. So that means that we have to convert from small xyz to big xyz. We should know what is the relationship. It's very important. Okay. So like this one. So big K, if you think it's a unit vector in the direction of big Z, then we should know how it is related to small ijk, small ijk. So we know that we have taken it in such a manner that, see, this Z at this instant is small z, or even the big Z, is in the plane of yz. Can you see? This is the z-axis, and y-axis is also in a vertical plane. It is also a vertical plane. Yz is a vertical plane wherein this big z-axis lie. Big z-axis is vertical. So if small yz is a vertical plane, so big z-axis will lie along in the same plane. So that's this big Z that's given by big K can be decomposed into two J and K. So that means that this is K and this is J, and the angle here is gamma. So with big Y, it is gamma. So that means that big Z, let's see, this big Z and Y. So that is, this is also is gamma. So with Y, it is subtending gamma, cos gamma, and with small z, it is subtending the other angle. Okay. So this is, so this way you should be able to figure out so how the vectors can be decomposed or rewritten. So because see, when you do the next one here, we have so many cross products and so many dot products and so on. So you have to bring all of them into the same, either small ijk or big ijk. So what we have here is that what? So the total angular velocity of the disk consists of omega naught, that is the spin about the small z axis. So that's omega naught k, small k. And then this is big omega, that is the angular velocity about the vertical axis of the whole system. So that will constitute so that means that big omega with big K. Okay. So this omega naught refers to 120 RPM, this big omega, how much is that? 60 RPM, right? Yeah. So the total assembly is rotating about 60 RPM. So these two should be added, but then they are referring to two different systems. So you have to bring them to same system so that you can do some operations. So that means that this big K can be written in terms of small jk. So you can add them. And then if you put down these numerical values, so everything is represented in terms of small ijk. So the total angular velocity of the disk, any point on the disk here, will be rotating with this kind of angular velocity. So that any point, okay, so we can find out the velocity about any point. Okay, so this is this is as far as the rotation is concerned. So now if you want angular acceleration of the disk, so we have seen that. So we have a constant small omega which is rotating with big omega about the z-axis. So any particle rotating with an angular velocity, so we can use the dot cross product and we can say that omega cross omega. Okay, so actually, so that means that this omega dot here, you should also see that we don't have, what else? We don't have any change in magnitude of omega, small omega. So the spin velocity is not changing. It's constant. So that is why this is coming only because of the change in direction. So this is only because of change in direction. So we can put the time derivative as this one. Otherwise, we also have to include the change in the angular velocity. So that is also would have been necessary. But since we don't have any change in magnitude of this small omega spin, so we'll simply have this as big omega cross small omega. So that is the cross product. And then you can go through this exercise of taking cross products. So everything is now in small ijk. So you can do this operation, cross product operation, and then you will get alpha as 68.4 I. Okay, so that's a little algebraic manipulation, right? So that's what we have then. So what we have finally is that we have the angular velocity of any point on the disk, and we have the angular acceleration of any point on the disk in terms of small ijk. I followed it? It's just not very difficult, right? Except that now we are dealing with all ijk. Okay, so like this, so this we already have discussed about the space cone and the body cone. So interestingly, so this is the total angular velocity, and we have small z here where we have small omega naught, and then about big Z we have big omega, and so this is the total vector sum of this one. So as far as the body is concerned, so all the points here, okay, they keep changing, and you can even think, see, in fact, if you go back, so I'll go back to this example. Yeah, in this example, how can you imagine that body cone is a cone? How is that with respect to the body? So how is this axis taking the shape? So we can do two things. Either you can completely think mathematically, or we can keep this n constant and rotate the body. If you rotate the body, what will the kind of shape it will have? It will have a conical shape, right? So that is what is the body cone is all about, right? So so if you can imagine that is the same thing here. Yeah, so that is the same thing here. So space cone and body cone. And here is the vectorial representation of the spin velocity along z, which is so much here, omega naught, and then there's so much here, about 2 pi radians of big omega. So these two, when you combine it, you get the small omega, which is here. Okay, so once you understand that, there are a few other things which you can calculate it. So once you understand the omega and alpha, so what you can see in this particular case, he asks you to find out what is the velocity of the linear velocity of point A. So if you want to find out the linear velocity of A, so what you need to do, as usual, you know that, is that what is that? We simply say it is omega cross RA. Okay, that's what we have to do here. Yeah. So if you want to find out the velocity of A, obviously with respect to the fixed point O, so what do we need? We need the position vector of A, so which is nothing but along y-axis, so much radius, and along z-axis about 0.25. So that distance is given. Along this z-axis, you are at a distance of 0.25, and along the radial direction, you have another 0.125 that is in the y direction. So that way, once you put this position vector 0.125j, 0.25k, so the next part is very familiar formula which we have. So it is nothing but V is equal to omega cross R, because this R is measured from the origin. So it is simply you will get the absolute velocity. So the absolute velocity here is omega cross R. Okay, so this is the linear velocity because R is measured from the fixed point. So, and that point O is the origin. Okay, so V is equal to omega cross R. So you can put omega, we know, we have R here, and then we can put the final in the vectorial form, you get 0.192 pi I. Okay, so this is the one which has gone there. So similarly, we can also get the acceleration. Okay, so the acceleration here of any point, we know that it is omega cross R and omega cross R, and you substitute it, okay, and you will get this. So that is only a matter of substitution and simplification. Okay. Okay. So it is more or less, you know, all the basics. Only thing is that now here it is in the vectorial form with all the three components. So please, I'll pass on these slides to you. Please examine them, go through each step, how the products are done. So this is about a cylinder, about a motor disc which gets input by two angular velocities. One is the frame, motor frame itself is rotating about the vertical axis, and after that the disc is rotating about the motor axis. So these two are combined, that's all. After that, it's only a matter of algebra. Okay, any questions? I mean, are you able to follow? I mean, you are saying that, okay, how about the non-inertial frames or rotating frames? We'll come to that also, we'll include that also. We are not having any velocity here in the rotating frame. In the rotating frame, point A is fixed, right? So that is why you are getting, see, what is this one here? There are, if you look at the rotating, what is the rotating frame velocity here? So you can even go through that also. You will get the same thing. So with respect to, are we fixing XYZ rigidly, small XYZ? We are not fixing small XYZ to the body. It is also rotating along with omega. So here we are not bringing that, but we'll bring that also a little later. So here we are not having any velocity with respect to the small XYZ frame. Okay, small XYZ is actually rotating along with the big XYZ. Okay. So if you are comfortable in doing the single body analysis. So this is a connected bodies. So if you recall, I'll just recall what we have done in the case of 2D. In the case of, this is similar to that. Let me just explain it to you. You did this in your tutorial. This is in 2D. So if you call this in 2D, we have a 4-bar mechanism. Here we have 4-bar mechanism in 3D. So, but if I just want you to recall how we did this analysis of 4-bar mechanism. For example, omega 1 is given to you, and we need to find omega 3. In that process, we can also get omega 2 also. Okay. So, all right. So how did we do this one? How did we do? So knowing omega 1, we can get the velocity of B. So velocity of B, we can get it as omega 1 K cross position vector B. Remember, this is what we did for A, for B, and similarly for C, this is unknown at this point. So this is completely known to us, but here omega 3 is unknown, which we need to find out here. And having this equation, how do we connect B and C? We know how to connect B and C. So the velocity of C is nothing but velocity of B with.
So camera is off. So
Sorry, camera is off. Oh,
yes.
Yeah. Okay. Yeah. Okay.
Yes, sir. Thank you, sir.
Oh, sure. Yeah. Keep telling it. So we keep switching, so we have problem. Thanks. Sorry. Yeah. Okay. So what I'm getting parallelly is that, so whatever we do in 2D, we are going to do similar thing for 3D also. So in 2D, what we did is that this is a 4-bar linkage. So given omega 1, we want to find omega 3. So the first thing is that we can get velocity of B, and similarly for velocity of C also we have this relationship. So then we can connect BC by this one. So this is omega 2 So you can see that having this relationship, we have 1 here, we have 2, and we have 3 here. So if you substitute 1 and 2 in 3, let us see how many unknowns and how many knowns are there. So if you substitute 1 and 2 into 3, so what we get here is that omega 3K. So this is on the left side, and VB is omega 1K. So this is substituting 1 and 2 in 3. So then what is that? This is one vector equation. What is given? We are given omega 1. All these position vectors we know at a particular instant. Okay. Given the configuration, we know all these position vectors. So what is that which we can solve here? So this is a vector equation which comes to 2 scalar equations. So we can solve for 2 unknowns, right? So that means that we can calculate. So we can, there are 2 unknowns. omega 3 as well as omega 2. So we can solve for this and this, right? So two scalar equations, we can solve for two unknowns, right? So this is as far as 2D is concerned. Okay, you have done this in your, did you do it in homework or? Okay, you did this exactly. So we use exactly the same concept to do the 3D analysis. So let us go back to the problem. Okay, so we'll go back to this problem. Can we remove this? Is this a hindrance for you? So what we do here is that we have two links. So can you say it is here? We have a link here, DA, right? And then we have AB link, and then we have another B2. In fact, the nomenclature is not exactly the same, but you can see exactly there are four, the one crank, and then there is another coupling rod and another crank here. So we have three moving links, though we call it as 4 bar. So the other 4 bar is actually D to C. Okay, so this is a space linkage, and we would like to exactly do this process. So what do we do here? So knowing the velocity of omega 1 here, what we are asked to find out is what is the velocity, sorry, no, given omega 1, we are supposed to find out omega 2, right? Given angular velocity omega 1 there, we need to find out omega 2. Okay, so exactly we follow the same procedure like this one, except that the angular velocities are vectors now, I mean 3-dimensional vectors. So for example, this omega 2 is a vector in the direction of x, y, z. So while this vector omega 1 is parallel to y-axis, so it is a direction y. Okay, so if you understand this, then there is a coupling, but this coupling is at an angle. It's not really at the x-axis or z-axis. So knowing these coordinates of A and knowing the coordinates of B, we can find out the position of A with respect to B or B with respect to A. So we will exactly do the same thing as this one. We'll exactly do this. So omega 1 is given. So we can find out velocity of B as, sorry, again, you're missing. I'll put back. You may not be able to see the board for the moment. Yeah. And velocity of B can be found out from C. So it is omega 1 cross, I'll put it as omega 1 B with C, B with C. And similarly, we can a B, or we'll call it as 3. All right, so having this exactly going on the same lines as 2D motion, so we'll exactly the same thing here, and so we will, yeah, we'll proceed further. Yeah, so this now you can see that fundamentally we are relating this one A with B, right? So finally that's the last equation which you put first, A with B, and then he knows what is the velocity of A and as 50 omega 2 j, because A is rotating about D, right? So that's what I've written here. And similarly, B is rotating about C. So that also is shown here. And then these two can be connected by, this is the cross product here, like omega 3, which he called as omega n. So he called it as, instead of omega 3, he called it as omega n. So this is 50 omega 2j, that's VA, and VB is 600I, and omega n cross RAB. So he put it as this product. Okay. Interestingly, this is the relationship. How many it will give you? It will give you 3 scalar equations. Now in 3 dimensions, it will give you 3 scalar equations. So how many unknowns are there? Can you count how many unknowns we can solve? We can solve for 3 scalar equations. You can make IJK equations. There seem to be 4, right? There is omega 2 here, and then omega nx and ny and omega nz. So there are 4 unknowns. So how do we get another 4th equation? So the thing here which you have to observe is that just like in 2D we have pin joints, here we have spherical joints. Here we have like cup and ball. Okay. Yeah. So that means that it is free to rotate because that kind of freedom is required. And then, so you have cup and ball arrangement in this joints at A and B. So how do we, what kind of, so it has a freedom. So what is that freedom? AB. So if you have a cup here, so that means that this rod can rotate, right, in this one. So similarly, if you have another cup here and it can rotate freely in that. So what does that mean? That means that along the line AB, it is free to rotate. Along the line AB, there is no constraint. There is no constraint. So it has a freedom to rotate about the AB axis. So in what way we can bring that mathematically? It has a freedom. Okay. So that means that this angular velocity vector Wnx and Wn, if you call it, so then if it has a component along AB, what does that mean? So it continues to rotate unhindered, right? It rotates unhindered eternally. So it is not supposed to, it cannot, it's a line and it cannot rotate its axis about line. A line cannot rotate about its own axis. So that way you can see this constraint. So this angular velocity vector along the direction AB, its dot product should be 0. So that means that its component along AB is 0. So that is the constraint, because AB is put as a one ball and socket joint and another ball and socket joint. So you can imagine that it can rotate freely about its own axis. So that means that eventually it cannot have any angular velocity component along AB. So that the dot product, that component omega n cross RAB is 0. So that leads to this condition. So you have 4 conditions and 4 unknowns. So you should be able to solve. So that's what he solved. So, okay. So we'll stop here.